You can handle the derivative of x squared, but how about 2 to the x? We're going to look at exponential functions, which are very important in modeling things like growth and decay, and be able to find out how we take the derivative, how we differentiate them. Let's begin with the derivative of the exponential function e to the x, which is really in a way the parent of all exponential functions. So this is a function that has a base of e, and we raise it to a power that's variable. We're going to find its derivative by using the limit definition of a derivative, which of course is, if you remember back from our origins of the derivative of a function is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. The change in the y over the change in the x as we get it infinitely small. And if we do this for e to the x, we get the derivative of e to the x is the limit as delta x approaches 0 of e to the x plus delta x power minus e to the x power over delta x. So what we're going to do now is we're going to factor out what the numerator has in common, which is e to the x. So we get the limit as delta x approaches 0 of e to the x times e to the delta x minus 1, which is what's left over delta x. And since e to the x doesn't have any delta x term into it, we can pull it to the outside. So this becomes e to the x times the limit as delta x approaches 0 of e to the delta x minus 1 over delta x. So we need to look at that function, because if we try to just do direct substitution and put 0 in for delta x, we would get a numerator of 0 because e to the 0 is 1, and 1 minus 1 is 0. Over 0, that's what's called the indeterminate form. So we have to look at another method at this point to be able to evaluate the limit as delta x approaches 0 of this. So we're going to graph this function e to the x minus 1 over x as x approaches 0. So the input is going to be x instead of delta x, just so we can visually see this kind of mini function that's a part of the definition of the derivative for e to the x. So if we were to graph this, we would find there was a hole at x equals 0. And that's what we expected, because we get 0 over 0 when x is equal to 0. But if you look graphically at this function, e to the x minus 1 over x, as x approaches 0 from the left, it's approaching a value of 1. As x approaches 0 from the right, it's also approaching a value of 1. So if you remember from our graphical exploration of limits, that is the definition of a limit. It's the value that a function is approaching as you approach it from the left and the right and get infinitely close to it. So clearly, graphically, and numerically, if we were to try to do it that way, the limit of this function is equal to 1. Therefore, if we substitute a 1 for this, the derivative of e to the x is equal to e to the x times 1, or just e to the x. So the derivative of e to the x with respect to x is e to the x. What an interesting thing. So if we wanted to find the derivative of a function like e to the x squared, the derivative of e to the x is e to the x. Well, the derivative of e to the u is e to the u du dx, using the chain rule. So if we wanted to find the derivative of e to the x squared, it would be e to the x squared, which is the e to the u part, times 2x, which is the derivative of u with respect to x. And if we simplified that, just to kind of put it in standard notational form, we would get 2x times e to the x squared. So the derivative of e to the u is equal to e to the u times the derivative of u with respect to x. Let's find the derivative of f of x equals x squared ex. Now we look at that and we realize it's a product of two things, so we're going to have to use the product rule here. So the derivative of this function is going to equal the derivative of the first part, the derivative of x squared is 2x, times the second part, plus in the second term we're going to use the first part times the derivative of the second part. Since we only have two parts, we can stop here. We can factor out what they have in common, which is an e to the x and an x. And so the derivative is equal to x times e to the x times what's left, which is 2 over here in this first term, plus x, which is what remains in the second term. So let's find the derivatives of exponential functions that have a base that's not e. What we're going to do is try and find a relationship between e to the x and any base of a to the x. So we're going to try to say a to the x equals some number times e to the x. And we'll call that number c. It's going to be a constant. We got to find that. So we're going to use a little bit of algebra here to try and find that value of c, which basically is a conversion factor between bases other than e and e. So using what we know about the algebra of exponential functions and logarithmic functions, we can rewrite this as x to the natural log of a equals cx times the natural log of e. Since we know the natural log of e is 1, this becomes a little bit more simple. And we get x times the natural log of a equals c times x. We can divide both sides by x, and we get the natural log of a equals c. Therefore, a to the x is equal to the natural log of a times e to the x. So the natural log of a is kind of our conversion factor between the two systems. And so if the derivative with respect to x of e to the x is equal to e to the x, it then follows that the derivative with respect to x of a to the x is that number c that we found, that conversion factor, times a to the x. And in fact, that becomes the definition of the derivative of a to the x, where the base is something other than e. The derivative with respect to x of a to the x is the natural log of a, that conversion factor, times a to the x. And this actually could be looked at as a much more general formula for all exponential functions, including e, because if we made a equal to e, the derivative with respect of x of e to the x equals the natural log of e, which by the way is just 1, times e to the x, which flows back in and becomes this just e to the x. So you can look on this formula as being a general rule for the derivative of any exponential function of any base, including e. It's equal to the natural log of the base times the base raised to the x power. So let's take the derivative of the function f of x equals 2 to the x power, an exponential function with base of 2, very common base used in binary systems. The derivative with respect to x, f prime of x, is going to be equal to the natural log of 2 times 2 to the x. The base is 2. So it becomes natural log of base times base to the x power. And if we use a calculator to evaluate the natural log of 2, we get that f prime of x is equal to approximately 0.6931 times 2 raised to the x power. So let's do a more complex example. Let's say a function g of t is equal to 10 raised to the t power over t squared. And we wanted to find the rate of change of g with respect to t. So g prime of t is equal to low d high minus high d low over the square of what's below. That's the quotient rule because this is the quotient of two smaller functions. So it is the bottom, the low part, t squared, times the derivative of the top part, which is the natural log of 10 times 10 raised to the t power, natural log of a times a to the x, minus the top part times the derivative of the bottom, low d high minus high d low, so we have 10 to the t power, times the derivative of the bottom, which is 2t, over the square of what's below, t squared raised to the second power. And we can simplify this a little bit. The denominator becomes t to the fourth. And so we can simplify this by factoring out a t and a 10 to the t power. And what we're left with in these two terms is the natural log of 10 times t minus 2, all over the t to the fourth. And we can take this a little further. So we can simplify that down by dividing t by t to the fourth. That becomes t to the minus 3, or t to the third in the denominator. So our final answer for this derivative is 10 raised to the t power times 2.3026, which is approximately the natural log of 10t, minus 2 over t to the third. So we've looked at how to find the derivatives of exponential functions, beginning with the parent function e to the x power, and then converting that to use for the derivatives of exponential functions with any base.